Hello, 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 Lila. Hello, Mansha. Hello, Tania. Hello, hello. Hello, Shen. Hello, Jaded. Okay, chat. Share follow me. What's it? Um, good after. Oh, can you hear? Oh, hello, Michael. Awesome.
Good
Hello,
afternoon, Chef.
and hello, Raymond. Okay, good afternoon, folks. Wait, are you guys together or no? Okay. Good afternoon, Luis. Good afternoon. Oh, and there's Sophia. Oh, we see this class is really good about I mean, really ahead of the curve on video. Thank you. Good afternoon, Luis. Good afternoon. So it's great to see you, Sophia. Hello, hi, Montserrat. Good afternoon, Camille. Shen, did you listen to the? Oh my God. Oh my God, that's hilarious. Okay, thank you, Shen. That's a portal. Points. Hello, Joyce. Wow, we really got some video going. Awesome. Thank you. Good afternoon, Leah. Wait. Oh, yeah. Am I saying Leah or Leah? Sorry, tell me. Good afternoon, Jerry. Hi, how are I'm good, thank you, Lila. Very good, very good, actually. Thank you. Good afternoon. I don't know why you'd ask. No, yes. Good afternoon, Tania, and hello, Nico. Okay, awesome, awesome. Oh, thank you for the smile. Okay. Okay. Wait, who am I missing? And am I saying Lee? Okay, okay. So back to business. I gather I forgot. Well, okay, back to business. Harmonic oscillation. What we're going to keep doing today, of course, at any time, if there's anything confusing going on with homework or anything, let me know in the chat. But I'm still, and I know many of you who handed in homework three. I mean, it was due, but awesome job. Like if you didn't get all the points, I think with homework three, I think I was fairly specific. Like if you didn't get all the points, it's because certain steps, maybe a diagram or something was missing. So just like go back and do the steps, and then you'll get all the points. One thing to be clear, whenever you hand in a new draft, it always has to subsume all the old drafts, if you know what I mean. Like every individual draft is complete unto itself. If that, so you don't, okay, I think that's clear. If it's not, let me know. But still, hello, hello, Nico. If I didn't say, I think I did. Um, so there's still an opportunity for everybody to get all the points on anything. We are in this situation now, there again, to remind you that in order to get all the points on something, you have to have at least turned in the first draft by the deadline, even if that deadline seems like ahead of the class material, which it often will. But I think you all get that again. If you, so it's great. I know you're up to already homework three, which is amazing because we're still going through homework two. But many of you already have caught on to the fact that by the time you do the first couple exercises in homework two, that's like the whole point. Homework three is just like almost a quick exercise practice review of the essence that we're trying to get out of these exercises that we're currently going over. So 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 we're going to progress. We're going to make more progress on homework two today. Um, By the time we get to that section with vectors and everything, vector multiplication, dot and cross, I'll make a decision. We need that stuff, but we need it for later. It's just I'm just so the whole point of homework two is to lay out all the math tools that we kind of need in general. So I may get back to the vector stuff later, depending on where we are with time. But um, so right now I'm just going to proceed. Oh, but the where we I believe we are. Well, our goal, let me put it this way. Our goal, we're going to go through the exercises of homework two that we're up to right now, pick up where we left off. The goal is to get the goal today, excuse me, is to get to the correct screen share. Wait. The goal today is to get to, come on, what's happening here? Is to get to the exercise. Have I lost? Oh, okay. Yes, the goal today is to get to problem 1F. Under part one derivatives, our goal is to get to F, where even though it looks like an arbitrary example, it shifts our attention toward toward a more general solution of the differential equation, a general solution that will start turning our attention to this concept called phase or phase constant. So what I'm saying is, what's the equation that's written on the board right here, it looks essentially like the same thing that we wrote last time. It says, if we have this certain differential equation, the differential equation for simple harmonic oscillation. If we have this differential equation for simple harmonic oscillation, then the solution is then a solution is a cosine function. But we're going to see today that the cosine solution we've been using works, but it may not be the only cosine solution. Maybe it can be more generalized. Maybe we can add a term to it. We're going to see. And when we add that term, it has physical significance, and it's called the phase constant. So we're trying to get up to exercise F today to see that. If we get no further, that's fine today. Okay, so we're going to pick up where we left off. I believe where we left off was, well, okay, so I'm going to switch the screen share for a second just to be clear where we are. Bear with me. And if there's anything in the chat, okay, where we are. Right, so where we are, and this is also, for the sake of the recording or whatever, like I believe, and stop me if I'm wrong, I believe that what we did was what you're staring in the screen right now. We did 1A, little Roman 1 and little Roman 2. And then I think we said the answer to be, like the point was, what we found was that x equals a cosine omega t is a solution to that second order differential equation. And what that means in English, well, what it means in English is well, this is how we talk about differential equations from now on. We note that differential equation is itself not an answer. Like you might be used to thinking of, oh, equations are what we need, and we plug into them to get answers to stuff. A differential equation is an equation. It's an equation that frequently comes directly from physics. Like that differential equation that's like on the board right now, d2x dt2 squared equals negative omega squared x. Like we didn't just make that up for math fun. That is a mathematical way of saying Hooke's law. It's f equals negative x plugged into f net equals ma, and recognizing that a is the second derivative of x. So that equation is really a physics statement. It's saying that something that's on a piece of elastic material will accelerate back home toward equilibrium at a rate that is directly proportional to how far it is from home. That is the mathematical way of describing what it means to be a restoring force. That the farther away you are from equilibrium, the harder you're pulled, and therefore the more intensely you accelerate toward equilibrium. That direct proportionality. The second rate of change of x is directly proportional to x. That's the mathematical essence of elasticity. So elasticity presents us with this differential relationship, right? And it has everything we want in it. It has a dependent variable, it has an independent variable, but it has them arranged in this funny way. So to get a solution to a differential equation means to somehow unpack it, and often that's difficult. And it's often non-algorithmic or like non-linear, like it takes like puzzle solving type skills to do it. But in our case, conjecture and verify. But to solve a differential equation or to find something that you believe to be a solution to the differential equation means finding a clear, direct, explicit expression of the dependent variable phrased as a function of the independent variable. Like to get a solution is to get x as a function of t that actually satisfies the differential requirement. So it's like Jeopardy. The differential equation, it's like differential equation is like the answer, and we're looking for the question that led to that answer, if you know what I mean. So we found we've now gone sort of forwards and backwards, and we're saying, okay, a cosine omega t is a solution. It satisfies d2x dt squared equals negative omega squared x, which in physics terms means, okay, once we know something is subject to an elastic force, then if we want to predict where it is as a function of time, which is like what we always want in physics, if we just want to know where is it when, then one way of doing that would be to let in Ravo. One way of doing that would be to say x is the following cosinusoidal function of t. Okay. And in the constants are arranged. So we found that it is a solution. It's this x equals a cosine omega t is a workable way to describe simple harmonic oscillation. That's what we found it to be. Okay. So now I'm going to go on to part so part of the way I'm trying to show this whole idea of is something a solution is it helps to see things that aren't necessarily solutions. If everything is a solution, that this is not a meaningful idea. So we go to C and we ask a different example. Okay, is x equal a cosine 5t a solution to d2x dt squared equals negative 3x wiring out? So I'm going to do that now. So again, if you were you would show the 5-step method again, but you could say, like, for steps that you're repeating from above, you could say C above, that's fine. I'm not going to do that now. I'm just going to like try to bang through answers. So I'm going to switch the screen. Hold on, I do this every time. I'm going to switch the screen and start writing. Hello, hello. Okay. Again, these are answers. These are not, even though you have to. Um, I'm just writing the steps that make it clear for me. Okay, so is something a solution to this differential equation? Like the bottom line, how do you know yes or no? You take derivatives, right? And this was how we originally got the cosine in the first place. Often this is puzzle solving again. In order to come up with a possible solution, you have to put thoughts together. Like there's some amount of educated guessing, some reference to lab work, like experience. To put a guess together is an art, not a science. It's an art of the science. But the reason it all ends up being mathematically precise and scientifically verifiable is that once you have a workable guess, you can find out if it actually works or not, if it actually solves or not, by taking derivatives. So that's what you always do. How many derivatives? Well, two, because it's a second order differential equation. Like it's so verify through derivatives always. So now we're going forward. Once you have the guess, you can like proceed forward, so to speak. Like if x equals a, sorry, oh, that is a, I'm sorry, is x equals a cosine 5t. I'm sorry. Right? If so, we're conjecturing that a cosine 5t is our solution. So then we take a first derivative, and I'm not going to show. So we explained how to do this last time. You got to use trigonometric derivatives, and you got to use chain rule, and you should review those if you're fuzzy on them, or and then talk to me or whatever. But so if I do it all in one fell swoop, I think the derivative is negative 5a sine 5t, right? That's the first derivative of that function. Okay, I'm sorry, I'm doing multiple screens here. Is there anything in the chat? Oh yeah, no problem. Sorry, I didn't mean to. Yeah. You're good. Direct chat. There's only one of you in direct chat. You're good. I didn't mean to. Yeah. Um, Uh, so that's the first derivative. So then we have to take the second derivative. Again, why? Because the whole point is the statement is that the second derivative bears a certain particular relation to the original function. So we have to see if it does. So the second derivative, I'm just recopying the first so it's clear. So dx dt equals negative 5. Sorry, someone's here. 1 second. Yeah, do I have the function right? Yeah, okay. So the second derivative, we just do the same thing again, right? Equals negative 25a cosine 5t, right? And note that, like, stop me if but you see, like, we're just doing calc 1 stuff here, but like the 5 gets squared, but the a does not. You see that, yes? And the negative sign gets introduced on the first derivative, but it doesn't go away on the second. Like, don't memorize that. Make sure you're clear on why that is. But the cosine comes back. I don't know if so. And bottom line, the reason the 5 came out twice is because the 5 is in there in parentheses. It's chain rule, but the a is just a constant. So just note, if you have, don't be ashamed to ask me privately if you're still fuzzy on those things. Like, maybe it's wise to ask me privately, sure, but let's nip these things in the bud now. This is all an opportunity to, like, you get my point. All right, so that's the second derivative. So what? What's the point? Well, one trick that I like to do is write it the way I did. Like, notice the order in which I wrote things, like this business right here should at least have the form that should look somewhat like the original X. Note the conjectured X was a cosine 3t, I believe. Uh, yeah, right. So that's like the right form, but that's not quite the same thing. What it seems to, so here it appears, did I do something wrong? No, sorry, that's not true. That's not true. The
It's
the no,
cosine 5t.
sorry, it's a 5. You're right. It's a 5. I'm sorry. It is a 5. I'm losing my mind. I wonder why. No, I'll explain at the end. Um, I will take 5 minutes at the end just to, like, fill you. I mean, most of you already know, but I just, like, want to be clear now that it's out in public, like in person. I'll just take 5 minutes at the end to make it clear on Zoom, like, what the heck is going on with my crazy life. So that's X. So I can say, like, okay, yeah, there's X. And I sort of intentionally always try to rewrite things so that I can see the X in the original. So here it seems that d2x dt squared equals negative 25x, right? So now pause for a second. Like, I'm sure most of you get this, but, like, so that is a differential equation. Like the cosine in general does solve that type of differential equation in general. And that type of different, like, I hope you see what I just did. I didn't rewrite the original differential equation. I'm literally noticing. I'm, like, noticing that, oh, when you take two derivatives of x, you do get a negative times a constant times the original X. Like, that's cool. That sounds like simple harmonic oscillation. And it is. And please let me say again, I'm not saying, I'm saying, oh, we did get not only a differential equation, but we got, like, the kind that we're concerned with here. The kind where the second time derivative of the dependent variable is equal to negative times a constant times the original variable. That's good. That's good. That's good. But as I'm sure many of you are noting, but wait a second. This is a differential equation, but it's not the one we were presented with, right? But in other words, or something like that. I think it was a 3, right? So what does that mean? It's not meant to confuse you, or it's meant to be a counterexample or to show you that. So what this means is thus, and I'll go back to that in a second if you want me to. If anybody tells me to, I will. Thus, x equals a cosine 5t. It certainly is a simple harmonic oscillator, right? It is like that. Yes, that is a simple harmonic oscillator. It does solve or satisfy uh, the diffie-q, the differential equation, for some SHO, but not this one, i.e., x equals a cosine 5t. It does not solve. In other words, so the answer is like no, it is not a solution. It does not solve. A cosine 5t, what it is it is a mass on the spring, but it's a spring vibrating at a different frequency from the one that we're asked to consider. You see what, like the omegas are different. That's the bottom line. It is a spring, but a spring of a different angular frequency and therefore different parameters. It's a spring, it's acting like a spring, but it's either a stiffer spring or a less stiff spring or a heavier spring or whatever than the one that we're asked to present or to consider. So, I mean, so in other words, just because something is a cosine doesn't mean that it satisfies the specific differential equation that we're looking at. To be a solution, it must be the case that when you differentiate twice, you get back the thing that you're supposed to. Quick note too, I think it happens later in the homework. The function x equals 1/2 at squared plus v naught t, like our favorite function from early physics 1 or whatever, like that's a function. That's a position time function, x depending on t. It's a great physics function. That function never will satisfy this differential equation. If you take x equal, and it's usually a question like on the midterm, if you take x equals 1/2 at squared or something like that and take two derivatives, the first derivative is at, right? Like just look at in your mind, x equals 1/2 at squared. You take a derivative once with respect to t, you get at, right? Like the 2 comes down and multiplies the half. So the first derivative is at. The second derivative is a. Now that's not wrong. That's like, I mean, the acceleration's constant, a, for something that could be described with x equals 1/2 at squared. That's why it's called a constant acceleration equation. It's not wrong. It's totally right. But x equals a is not d2x dt squared equals blah, 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 x. In other words, we're looking for things where the second derivative brings us back to the function, not brings back to a variable, in other words, doesn't bring us back to a constant. So no situation will x equals 1/2 at squared ever be a solution to our differential equation. You can never use it to describe a simple harmonic oscillator. Maybe I should have asked that first, but I didn't. I just jumped to something that looked like it might, but still doesn't. So some things solve and some things don't, and you have to take derivatives to see whether they do or not. So that's that one. If there's, I'm going to go on. Stop me. You're welcome to stop me or ask me to go back a page. But other than that, I'm going to go on. Okay, so I'm going on to the next. Well, I'll go on to the next one. Let's see what the next one is. Okay, now it gets a little like repetitive in a way. I mean, so I'm just going to scroll these. So now it's just asking you to practice in a way. Like, well, actually, what's even stupider in a way now, D is actually just asking you to do the work to justify or see what I just did in C. In fact, that's what I did, right? Like, I think with your permission, D, we just did it. We just did it all. So it's kind of just showing you that you have to be flexible about whether you're going forwards or backwards with differential equations because they are intrinsically sort of reverse engineering. So you are just sort of going backwards and forwards on them until you get used to it. Okay, so I'm going to go to E. Unless if you have a problem, no shame. If you have an issue, let me know. But I'm going to go to E. E. Now, what's going on here? Same deal, but now it's trying to make it look more like physics, right? Like the above was just sort of random math, and now it's saying like, oh, it's also trying to stress a constant just means a constant, means something that doesn't change. Whether it's a clear number like 5 or 3, or it's a symbol like omega, or it's a set of symbols like k and m. Like a k is a constant, like a constant divided by another constant is a constant, whether we offhand know what it is or not, right? So now it's trying to show where that so I'm going to do this quickly. I think you've now seen this in last class in a way. um oh, and I know the numbering got weird, sorry, but so just so now there's physics parameters. The ultimate lesson here is no matter if physics expressions can get super, super long and complicated looking, but if you're always trying to track what is the independent variable, what is the dependent variable, what are constants, even if there's a million constants, which there turn out to be a million constants in a lot of physics equations because we're referring to a bunch of physical material properties. But if they're all a bunch of constants, don't let them intimidate you. Just package them together in your mind as one big constant. That's really what's going on here. So then I'm just going to follow the Roman numerals. Then dx dt, same thing. Chain rule and trigonometric derivatives equals negative a sine. Oh, sorry, no, totally kidding. Let me get myself a room. I just need more. Equals negative a. I did it again. Chemo. Not really. Right? That's the first derivative. Stop me if you don't like it or agree or whatever. But that's the first derivative. And the second derivative, I'll do on the second page. Hold on, I'm going back and forth. Screen going to see if this. Sorry, I do that I always say I can go back. Yes, I can go back. I'm sorry, I do that because I'm going back and forth between screens, so I didn't see it. Is this the page you want or the one before it?
Um, just the one before it, please.
Sure, absolutely.
Okay, perfect.
Okay.
I'm just gonna take a picture so you can move on with your
Okay,
notes, okay?
you're the best. You're an officer and a gentleman. Thank you. Okay.
All right, beautiful. I got
All
my
right.
picture. Thank you.
Thank you. Okay. I hope the PDF smiled for you. Okay. We should teach PDFs how to take selfies. Okay. So that's the first derivative. Now I'm going to just write it above on the top and take the second derivative. So here's the first derivative, negative a. Okay. So now I take the second derivative. I just do it again. So chain rule, the square root of km thing comes out again. So I have a k over m. No, now, well, yeah, okay. Cosine, because derivative of cosine is cosine of that stuff. And then here I'm going to take the liberty. I'm going to get in the habit. I'm going to, because this is all multiplication, like the a times k over n, it's all times cosine. It's all multiplication. So multiplication is commutative. So I can take the liberty of going like this. And that's a good habit to get into when you write these second derivatives, because now I can identify. So that's the second derivative. And that's all it's asking in part 4 or whatever. Yeah, that's all it's asking. Oh, and it doesn't even ask so it doesn't even ask the sort of obvious important question. I mean, technically that's my answer then, I guess. But why did I just do that? Because note, then in this case, d2x dt squared equals, like, it does equal, actually, well, so if you were to call this something such as omega, then this would be omega squared, right? And therefore, and therefore, this expression is a solution to, or satisfies, or solves, all the same thing, solves this. This is we already did this last week. I'm just doing it in a different way. What I'm trying to say again is the bottom line, and those of you who turned in homework 3 already, I think really seem to see the following bottom line is that there's all kinds of differential equations in the world. We're not here to study all of them just for fun. We're here to study the ones that are popping out of physics at us. The one that's popping out of physics at us in this context right now says second time derivative equals negative constant times original function. What we're saying is the solution to that is a cosine function for which the angular frequency, like the constant inside the cosine function, must be the square root of whatever the original constant was in the differential equation, right? Like here, like if 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 the piece inside the cosine was square root of k over m, that works as long as what's outside the whole diffie q is the square of that. I'm not making this any clearer. Oh, the, the reason so so the reason you keep seeing this differential equation written as a da 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 equals negative omega squared, don't that's just a constant being squared. So it's still just a constant. We could have called it anything. We could have called it k over m. We could call it beta. We could call it anything, but we call it omega squared because we're getting used to the fact we're anticipating that whatever that number is, the omega that's going to appear in the cosine solution is going to be the square root of it. So we call it omega squared. I don't know if that helps or not, but that's what we're just trying to say. And if the physical, and that omega is always comes from parameters, material properties of the physical system that is oscillating. If it's literally a mass on a literal spring, then the properties are K and M. If it happened to be a pendulum, like with a length of a string in a gravity field, then the parameters would be lowercase g and lowercase l. I think you see that or will see that, or I've seen that in lab. If it's something else, it's something else. But the constant, the angular frequency is always the square root of the original constant in the diffie q. And that original constant is determined the minute we know the ingredients of our oscillator. It doesn't matter how it's set up, it just matters what the ingredients are. Like that's the theme here. Okay, so this is a solution. So okay, enough. I stop me, but I think that's enough of that. Because now we're up to F. I'm just looking in the chat. Okay, he's good. Okay, all right, so now we go. It gets a little deeper now. A little. So we go to F. So I'll slow down a little bit. Oh, and also please note, if I have not made this clear, you should note in your notes. Were you well, first of all of these are X's so far in this homework because we're trying to refer back to the physics situation where we're on an X-axis. But if I ever use Z, I'm not changing the math. I'm trying to stress that the math works whether or not you're on an X-axis, whether or not you're studying something literally moving across meters of one-dimensional space, or radians across a curved arc in a pendulum, or electrical field intensity or current in a circuit. Like if when I use Z, it's all the same math, but I'm trying to emphasize it doesn't, no matter what kind of physical system it is, this all works. Okay, so ZX, you should be able to move fluidly or whatever, or in homework 3, it's D, whatever. It's whatever the dependent variable is, has to obey all this stuff. But the other thing for your notes or whatever is please note that I'm using the terms like capital A and X naught or capital A and Z naught. I'm using those ultimately interchangeably. They don't mean the same thing, but they turn out to have the same value in all these cases. So just quick, just to be, I don't want to rabbit hole, so I'm just going to say it and hopefully you can write it down. Like, like X naught stands for initial displacement from equilibrium, right? X naught is the initial, the, the initial value of displacement from equilibrium. A technically stands for amplitude, which technically means maximum displacement from equilibrium. They don't mean the same thing. Like where you start doesn't mean the same thing as like how far you ever get. But if you understand homework 1 and how energy conservation is necessarily occurring during any of these harmonic oscillators, like harmonic oscillator means energy conservation. That's part of the principle of homework 1B. Then it turns out wherever you start is the farthest you're ever going to get. If what we mean by where you start is the place that you are where you have zero velocity. Like it doesn't have to start like the Big Bang or something. What do I mean by start? I mean the place where we start paying attention, and note that the thing doesn't have any velocity yet. Okay. So A and X naught are two names ultimately for the same quantity, or two conceptual ways of looking at the same quantity. Okay, that's just to be. So we have X equals A cosine omega t plus 3.5. That's our given. Now I'm going to say right away, 3.5 is just some arbitrary weird number. It's an arbitrary, I could have, there's no significance to the fact that it's 3.5. It could have been 7, whatever. It's just a number. The significance is that it's a number being stuck into the cosine argument, and it's a constant. It's like, well, it's arbitrary, but what's important about it is where it is and the fact that it's not changing. Okay, and we're asked to take two derivatives. So I'm going to take two derivatives. Okay, so right now it's just like raw math. So I'm going to do it. And the Roman numerals are messed up again for reasons that have nothing to do with chemotherapy. Because this sheet was made a long time ago by me in some other kind of trance. Okay, so what's the first derivative? Chain rule, yada, yada, yada. It is, oh, whoa, so let me be careful. So I've got it. Of course, it's going to be a negative sign. And of course, I'm going to do chain rule, but now I'm going to be careful for a second. Chain rule means take the derivative of what's in the inside of the parentheses. What's inside the parentheses is omega t plus a constant, like a number that doesn't change, comma, yo. So it's like writing y, it's like in the parentheses, we have like mx plus b in effect. Like, what's what's dy dx of mx plus b? Well, it's m plus 0. Stop me if you don't buy that, please, or privately if you don't want to. But I think the derivative. So in other words, like however you think about it, like this is like a straight line. The derivative of it is the slope. The derivative doesn't change. The slope doesn't change depending on the y-intercept. Or I'm making it harder than it is, I'm sure. The point is the derivative of the inside is just omega. It's not omega plus 3.5. It's not omega times 3.5. It's omega. Because the derivative of 3.5 is 0. So the derivative of that doesn't mean I'm ignoring the 3.5. It just means it's not affecting it's not affecting the chain rule. So I'd say the derivative is negative a omega sine omega t plus 3.5. So the 3.5 is there. It's getting carried along for the ride, but it's not coming out. I can't say it more clear. So then if I do another derivative, same thing's going to happen again. The omega is going to come out again, but that's it. No 3.5. And we'll get this. And again, there's no significance to the 3.5 other than this number. I'm just switching screens to see if there's anything in the channel. I'm sorry. Okay. So what does this show? Well, first of all, it shows we just got two answers, so that's more homework done. Um, but then the real question is G, and I can go back if you would like. I will watch the chat. Am I lying? I'm lying. I will look at the chat. I can go back if you want. But G says is. Well, at first blush, you might say, like, now that so the point of this exercise is the other exercise showed that just because something's a cosine doesn't mean it automatically satisfies. We have a cosine here, but it looks a little funkadelic. Like there's a little more to like 3.5. Vasti says 3.5. Who asked for a 3.5? So it's very reasonable to think like, I think the 3.5 is screwing thing up. This is not the solution we talked about last week. But what we just showed is I mean, if you go back, like, oh, I should have, all right, here. Like what we just showed, I'm just writing it. Okay, we just showed this, the bottom line on the page, but multiplication's commutative. So I can rearrange. So there's two constants out in front, like A is a constant, omega squared is a constant. Let me just shift their order to make clear what's going on. We just showed, so evidently, d2x dt squared equals negative omega squared A cosine omega t plus 3.5. So evidently, even when we threw the 3.5 in, because of the nature of where we put it, it preserved x and it didn't screw up the derivative of x. It didn't alter the derivative of x. So and please stop me if you don't see this. There would be no shame. This is a new point. I mean, it's not a huge, well, it's a subtlety, but we're now saying, wait a minute. Apparently, there are more complicated cosine functions that will also work. That's what we're saying. We're saying that up until, okay, I'll write it. I'll even be more general now. Okay, so in general, what we've been saying and what's on the front of the board or today and last week, I'm saying, so we're moving forward now. I'm saying up until now, what you want to get used to is if you are walking through the forest and you slam into the differential equation for oscillation, d2z dt squared equals negative omega squared z. If you're thinking, oh, what might solve that differential equation? What we've been saying is, well, z equals z naught cosine omega t will work, and it will. So we've been saying that's a solution, but I want you to now know we've been saying it's a solution. We're not saying it's the solution. We're not saying it's the only one. We're not saying it's the most general way to put it. It's a particular solution. In fact, it's the specific case. What we're saying now is, and pause for this. So what I'm saying now, the 3.5 was just an example. Could have been any number. Any number. Frankly, it could have even been a negative number, but then it could, yeah, it could be any number. As long as the numbers doesn't change. Any number we would put in that place in the cosine argument would not mess up the derivatives. Therefore, when we've been saying z naught cosine omega t or x naught or a cosine omega t and just leaving it, what we were really, without realizing, what we were tacitly doing is thinking of the special case where the constant being added was zero, right? Like it doesn't contradict what we've been doing, and what we were doing doesn't contradict this. It's just that what we were calling a solution was a special case solution where the constant that was being added was zero. So we didn't even think about a constant being added. I'm going to say from now on, there could be any constant mathematically. There could be any constant there at all. And from now on, we designate that constant with the lowercase Greek letter phi or phi. I say phi. Which is like an upside down, it's like a theta rotated pi over 2 radians. Right. So that's a phi, that yellow thing. And it stands for any constant. And oh yeah, I hear you, direct chat person. I thank you. Okay. Yeah, I'm sorry. Okay. The units. So it could be any constant, and we're going to give it a name in a second, but we symbolize it with phi. And it mathematically has to be there, but I wouldn't care. But for the fact that if it mathematically means something, that it's got to be representing something in the physical world. It has physical significance that we now have to explore. But in order to explore that physical significance, I'm going to pause for a second and ask you. Whenever I use square brackets, I mean to look at units, like that's like a notation thing. If I'm putting square brackets, I'm about to say something about the units of a variable or of a measurement. So I want to ask you, just based on the nature of cosines and everything we're saying, that 3.5, even if it was arbitrary, what units must it have been measured in? What units must this thing, this constant, it could be any number, but it's got to be a number of what's. So if you want to put in direct chat, in fact, please do. If you have any thought at all, I'll repeat the question. In fact, I'm going to say, because we have a minute or two. I'm going to say I want everybody's participation on this, unless you're like riding on a subway right now or whatever. But oh, great, great. So I'm already seeing. Oh, and I meant to say, I should say, put in direct chat, please. So I see some things in the group chat, which is great, fine, fine. But on a thing like this, I'm not saying right or wrong. I'm just saying yay that you put in participation. Everybody put an answer in the direct chat, or but like I understand the question, but I don't have an answer. That's fine. Or honestly say, I missed the question. Can you repeat? But like everybody say something indirect, please. And I'll wait till I get them all. and then but I'm seeing things that's great. And I understand some people in the group chat, that's fine too. You don't know that they're necessarily right. Like don't be or whatever. Like I mean, you could be influenced by them if you want, but so I'm looking, there's direct chat, great, 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 great. Hold on, more people coming in also. Hold on, I'm looking, great, great, great. I'm not sure of the answer, fine. But if you say I'm not sure, okay, okay, fine, fine. Oh, okay, and I'll repeat the question. So the question is this, I'm saying from now on, backtrack the cosine thing that we're working with, the cosine expression, the cosine solution, actually can be more general than we thought. There can be an extra number, there should be an extra number, a constant stuck in to the argument of the cosine function, and everything will still work. In other words, physically, so I haven't repeated the question yet, I will. Physically, if you want to describe a simple harmonic oscillator, a more general way to describe it is like constant times cosine of omega t plus a constant. Like that's the more general way to capture the nature of an oscillator. I'm saying we're allowed to stick in a number. We should stick in an extra number. It might be zero, but it doesn't need to be zero into our cosine function, and it'll still make all this math work. So my question is, if we're sticking an extra constant number, here's my question. If we're sticking an extra constant number into the parentheses of the cosine, what units must that extra number be measured in? What must be the units of this new term that we're now looking at? And don't listen to me, guys. Okay, so that's my repeated question. So I want everybody to, like, I know how many there are of you. I want everybody to say something in direct chat, even if it is, I get the question, but I'm clueless. Like, which I don't believe you really are. I bet I could get you to be on clueless, but I won't. But I won't. Just let me know that you're still with me. Cool. Oh, and so actually there's various. Now I'm seeing this is good. The fact that I just clarified the question just got me a lot more answers, and they're actually varied, which means this is worth it. Okay, okay. And I don't, and I'm saying clueless like the way you, I don't believe any of you like really clueless, but okay. But you understand. Okay. I think I've now heard from everybody. I'm just checking. I think I've heard from everybody, except people that are on the subway or whatever. Okay, fair enough. Okay, fair enough. I love that. I get the question, but not sure about the answer. And you can submit all that for points. Okay, so I actually got various answers, a tad bit. Okay. Well, I didn't say a name, right? I got various answers. Which shows this might be work. But to cut to the chase, yes, I do believe the ultimate correct answer. And by the way, if you wrote a wrong answer, remember, you whether you wrote anything, you submit to the right or wrong portal. If you wrote anything, you get points, and that's called right or wrong because you took a risk. If you actually got it wrong, you literally can get extra points by having the guts and the honesty to submit into the wrong portal. Remember that. You get extra points for being wrong. I know it's crazy, and that's not the chemo speaking. Like we could whatever. So please participate. Okay, so don't be ashamed when I tell you or embarrassed when I tell you. Yes, the answer actually was radians, as in fact some people whose name might or might not rhyme with Schmeichel definitely did say at the beginning, but of course just because he said it doesn't mean it's right, but it is right, and he did say it. Radians is, and a lot of other people did too. Thank you. The answer is radians. Why am I making a big deal? Well, first of all, why is it radians? Because there's two reasons. Well, so I'll write it. So the answer is radians, and this will be important in our life. Units are the way we turn the math into the science, right? It's not like a detail. It's like how these relations become start talking about measurements in the lab. So the units of this thing, phi. Oh, and we're going to call this from now on. This is called, as it said on the front page. This is called the phase. This is called the phase constant. The phase constant is a number measured in radians. First of all, why? Well, for one thing, omega times t had to be in radians, right? Like, and by the way, if you got the wrong answer, please listen to me now and then honestly tell me if you get it after I say it. There's no shame in being wrong, but let's see if this makes sense to you. Omega times t already had to be in radians. Omega was designed to make sure that omega times t was in radians because you can only take the cosine of something measured in radians. So omega was radians per second. Like omega, so many of you guessed radians per second. Very, very educated, reasonable guess. But because omega is in radians per second, you're correct. Omega is a frequency, angular frequency, but it's omega per second to multiply by the seconds in t. So it's omega per seconds times seconds makes radians. So you can take the cosine of that. Now, if we're going to add something to that, first of all, the only thing you can add to radians is more radians. Like literally, you can add pounds to pounds, but you can't add meters to pounds. You can multiply meters by pounds, which is weird, but you cannot add meters to pounds. So the only thing you could add to radians would be more radians. That's number one. Number two, when you add them all together, what do you get? You get a lot of radians. And that's the only thing that the whole parentheses could be if we're taking the cosine of it. So omega is like itself radians. Like there's no seconds involved. It's just radians. Omega has to be in radians. Now, why do I care? Because that tells me something about the significance, the physical meaning of omega. Okay, so I'm saying in English is, oh, oh, oh. So at least one person in direct chat has like written "oh," which I think implies she or he understands what I'm saying now, which is terrific. That means we're getting our money's worth. I appreciate that if that's what you mean. And here's what I'm saying to everybody. And I'm just going to change the view of the screen. Sorry. Okay. What I'm saying is phi, the phase constant, is an initial condition. It's a condition. It's not a parameter. It's measuring where we started measuring the oscillations. It's measuring how far into the cycle, into a cycle, the oscillator was when we started our stopwatch. Because remember, a radian ultimately is a sixth of a cycle. So, um, so, 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 for example, but that's what it is. It's the head start or the delay of the oscillator. It's like where the oscillator was when we started measuring, but not where it was like how many meters or something, because like that's not ultimately that would totally that's not we're not interested in raw meters anymore. We're interested in cycles now in an oscillator. So it's how far along it already was into a cycle or how not far it was into a cycle. And the way we measure that is with radians. So for example, so So I'm going to analyze this now. Like if we now think of oscillators as not just cosine omega t, but cosine omega t plus phi, plus some arbitrary phi, like what is the impact of that? Like what does that mean? So then case one, let's say, the case that we'd been studying before we knew about this, when phi equals zero, right? Like which we've been tacitly assuming until now. When phi equals zero, what that means is um at t equals zero, z equals z naught cosine omega times zero plus zero, right? I'm just plugging in. If you look at the case when phi is zero, then let's look at what happens at the beginning. Like where is the oscillator at the beginning? At the beginning at t equals zero. So I'm just plugging in zero for phi and I'm plugging in zero for t. So I get I'm plugging into the function. So z equals z naught cosine of 0 plus 0, i.e. cosine of 0. And you know cosine of 0 is 1. Oh, great. Direct chat person, by the way. Sine of 0 is 0. Sine of 0 is 0. Sine is super. Cosine is crappy or counterintuitive, right? Sine is super. Sine of 0 is 0. It's a sine of 0 is 0. Memorize. Like picture the unit circle. Therefore, cosine is crappy, is counterintuitive. Cosine of 0 is 1. So cosine of 0 is 1. That's why we like cosines for the if you think of okay. So this looks like a bunch of nonsense, but what I'm saying is, when phi is 0, that's the most direct, like non-fancy thing that you did in the lab. When phi is 0, it means we started our timer when the oscillator was at an amplitude position, like at the maximum, at the begin, the easiest place to consider the beginning of the cycle, the turning point, right? The end point. Like when phi is 0, that means, so when there is no phase constant, when there is no head start or delay, when phi equals 0, we started our timer. Our timer when z was at amplitude, positive amplitude technically. Right. Okay, I'm interchangeably saying z naught a, same thing, right? But you see how in contrast, and I'll go back in again if you want to, and I am watching the time. We got 11 minutes, which really means about 6 because I'll take 5 minutes at the end. So what was that? Case 2, same function, right? Z equals z naught cosine omega t plus phi. But let's what let's test what it means when phi equals, oh, I don't know, say pi over 2 radians, for example. This is an example. But that's the kind of thing, like 3.5 is kind of just a number just to get you rolling, but generally they'd be like, multiples of pi or whatever. They don't have to be, but they often would be. Say phi equals pi over 2 radians. What does that mean? Then plugging in, I'm just plugging, then I should say, then at t equals 0. So this is all about where we started timing. Like that's why I'm plugging in t0. It's the whole point of the phase constant is like, what's the initial condition? That's what it is, an initial condition. So at t equals 0, plugging in, z would equal z naught cosine omega times 0, but plus pi over 2, right? Because you see what I'm doing, right? So um and this is an omega. It's illegible. So z equals z naught. I'm just plugging 0 plus pi over 2. So z equals z naught cosine pi over 2. Now, cosine of pi over 2. Now, what's that? Now, picture the unit circle. Remember, and by the way, resurrect the unit circle from your, like, dust off those notebooks from wherever, get out that, it's all about the unit circle. Whatever, or get it tattooed on the inside of your eyelid so that you see. That's gross. But every time you blink, you'd see it. That's gross. Okay, sorry. Um, what is the cosine of omega of pi over 2 radians? Well, pi over 2 radians, it all comes back to 2 pi radians is a full cycle. 2 pi radians is a full cycle because circumference of a circle is 2 pi r. 2 pi radians is a full cycle. So, and a full cycle means there and back. So pi radians is a half cycle. That means just there. So pi over 2 means a quarter cycle. It means from the beginning to equilibrium, right? Bear with, or on the circle, I'm sorry, I said unit circle. So on a circle, pi over 2 radians means like 90 degrees. Like you start here, you start there on the unit circle, and then you're going up, 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 up. That's 90 degrees. That's pi. Uh, um, really awesome what someone just wrote. So someone wrote in the direct chat, 0.5. 0.5 in a way, 0.5 of a cycle. Yes. Or, well, wait. Yeah. Well, I think I know what you mean by 0.5, but let's be careful. That's awesome. And please submit that for double points. But let me be, and I'm looking at the time. Pi over 2 radians means like 90 degrees on the unit circle, which means we're looking at the top of the circle and we're asking what the cosine at the top of the circle, i.e. the x coordinate, like how far over are we in either on the x-axis if we're at the top of the circle or, well, yeah, that's really what we're asking. Like, so I guess what I'm trying to say is the cosine of pi over 2 radians means the cosine of 90 degrees. And I believe that if the cosine of 0 is 1, because that's the x coordinate at, yes, good, direct chat person. Oh, you totally just, that's awesome, direct chat person. Like you could submit for like a bajillion points now. And I really like education just occurred, or awesome self calibration. Yes, what the direct chat person has said is 0. The cosine of pi over 2 is 0. And the significance of that's awesome, really. And it really shows you're really with me. And we're going to end on that for them. I mean, we're going to, yeah, we're going to close down shop on that. But what does this mean? It means that if you have a this is just an example to show what phase constant means. But if the phase constant of an oscillator is pi over 2 radians, that's a way of saying the oscillator started, or we started our timing when the oscillator was already kind of in the inconvenient but interesting position of already being a quarter of the way into its cycle. Where did I get a quarter? Because a full cycle is 2 pi radians. So pi over 2 is a quarter cycle. Like pi radians would be a half cycle. Pi over 2 radians is a quarter cycle. And physically, what does a quarter cycle mean? It's all like homework 1B, like that original picture. It means that when we started our timer, the thing wasn't at an amplitude position. It was, and it wasn't on the negative amplitude either. It was right in between at the equilibrium. When we started our timing, it was already at equilibrium. Can we do that? Sure. It's like actually harder, but we could do that. And if we did do it, we would note that with this phase constant. That's the deal with the phase constant. I'm going to say one last thing. Please write it down. This phase constant idea would be stupid and unnecessary if we only ever had one oscillator. Because if you were only, and this is why it didn't come up yet in the lab or anything. If you only have one oscillator, it's much more convenient. You can start your timing whenever you want. So that what everybody would want to do and would do is start their timing when the thing is slowest, or when it definitively, you let it go for a while and you click your stopwatch at that obvious point when it's turning around. It's the easiest point to catch. So you would naturally always make phi 0, which is why we started with that case. But the reason sometimes you wouldn't, the reason we have to track this constant from here on in is because of the possibility of having multiple oscillators. If you have a bunch of oscillators and they're all doing the same thing, but they didn't all start but if one started, if they're all out of phase with each other, you can't start your stopwatch at the same time for all of them. But you know what I'm saying? So the purpose of this is to measure where one oscillator is relative to or compared to each other oscillator. So this becomes crucially important when we put oscillators together in a multiplicity. And that's where we're going with this. The purpose of all this, now that we understand the math of an oscillator, we start spreading out or collecting oscillators, putting them together and putting them all into an interesting phase pattern. And from that, we build what are known as waves. And a wave is an unthingy thing, which I've never even yet defined for you. So the next class, we're going to take a left turn. You have plenty of time to do the homework because I've got to do that unthingy thing sheet with you, which I never have yet. Anyway, this is heading towards making a wave, which is really the central focus of the class. I'm going to pause for a second. We have 3 minutes. I'm going to pause for a second and I can hang out, but don't go, please. Let me just pause. I'm going to turn off the recording.